Hello, today I'll give you a small overview about the methodology for system engineering using Enterprise Architect. We named it EnArSys. I'm Roman Bretz and I'm working for Liber Software GmbH. It is an Austrian company based in Vienna. We are a preferred partner of Spark Systems and a contributing member of the OMG. Let me start with a small outline of the presentation. We'll begin with terms definition and the introduction of EnArSys, and followed by an example developed with the EnArSys methodology. We will start with system requirements and traceability aspects, followed by use case analysis and system context diagram. Then we'll continue with the analysis of use cases using sequence diagrams. We will talk about state machines and activities, and after that we'll switch to the architectural aspects, to the functional architecture, to the architecture of processing chains, and finally to the physical architecture. The system engineering is a very complex topic and multi-dimensional topic. On the other hand, on the one hand, there is several engineering domains like mechanical engineering, electrical engineering, software engineering. And on the other hand, there are several aspects like requirements, system behavior, and system architecture. To cover all these aspects and all these domains, to be able to manage all this information you develop over the time, you need also tool support. Enterprise Architect provides a capability for model-based engineering and allows to prevent redundancy and covers the traceability aspects very well. This slide provides us an overview, an impression of the model developed by the EnArSys methodology. You see here different system engineering aspects like the behavior, system behavior, represented by states, system states and activities, and the function and the architecture aspects, functional architecture, processing chain architecture, and the physical architecture. All these elements are connected with each other, so you're able to build the traceability through the whole model. Before start with the system engineering, you need to answer some questions and separate the concerns. The first question you need to answer is what notation you will want to use for the modeling. Is it UML, SysML, BPMN, or probably something different? The next question will be the tool. Of course, you have already tools, and now you need a next tool for model-based system engineering. Maybe you design systems using Microsoft Office, but the tools like Enterprise Architect provide definitely some advantages. Of course, you also need to know what process you will use: Agile process, V process, or something else. And last but not least, there is a question of the methodology. The methodology defines the steps you need to go through the definition process. What you have to define first? what is based on what, and so on in your model. Sometimes people think the language or the tool will also provide the methodology, but typically it's not the case. Basically, it is your task to define the model content, to decide the model structure, how the model will be structured. Probably some modeling guidelines could be helpful if you need to generate documentation or code out of your model. You need probably to adapt the templates, and probably also UML profile could be helpful. This slide give a very good overview also about the expertise of our company. We are focused on the notations, tools, and methodology. We have experts in different languages. Of course, we are expert of Enterprise Architect and other tools, and we developed the methodology could help you developing the systems. Let me introduce the EnArSys methodology itself. It is based on the 3 system engineering aspects: system requirements, system behavior, and system architecture. All these 3 aspects are covered by the methodology, and you will step by step go through this, or will cover all these aspects. So now let us begin with our example. We have a development order. We need to develop a device that is able to sense its environmental temperature and to display the current value on a text display. All in one, we need to develop a thermometer. As usual, let us start with requirements. In our case, requirements are not text topics, but rather the model elements, and they have typically hierarchical structure. The requirements during the system development, the requirements will be connected to the architectural and behavioral model elements. Why? We should connect them? The reason is the traceability. The basis for the traceability is the amount of all the relations between the requirements and other element types, and between the elements themselves. And that's throughout the whole model. If first requirements are available, we can start with the use case analysis. Use cases provide the entry point or other entry point for the behavioral analysis. Use cases are very useful for understanding the system scope and also for communication of the system scope. Use cases answer the question, who needs what from my system and what external systems we need for providing the required functionality. So it is important to name the use cases always from the primary actor point of view. What is basically an actor? Actors are the system neighbors on the same abstraction level. It means also they can be also technical systems. And if you're on the deeper level of system definition, it could be possible that you have only the technical systems and no human actors at all around you. The system context diagram is the entry point into architectural analysis. The system context diagram focuses on the system environment. and answer the question who and how is connected to my system. A use case diagram and system context diagram shows basically the same system neighbors, but they name they're different. They name this neighbor systems different. Use case diagram names them actors independently if you speak about systems or humans, and system context diagram names them external systems and users. So I told already about behavior, but what is behavior? Typically, if I look at models developed different companies, architectural aspects and requirements are covered typically very well, but the behaviors, the system behaviors, not really. Here you see the typical representation of a class of a block in a model. Class has some attributes and some operations. That's it. But SysML or UML defines more. A class or a block, it's much more than just a collection of attributes and method signatures, methods or operations. Operation is a method signature. An element may contains and encapsulates their behavior. And the behavior could be modeled using state machines, activities, and interactions using, again, sequence diagrams. The behavior can be standalone, can be instantiated by itself, or they can be the implementation of the operations. And in that case, the operation is connected to doing behavior. And it's very similar to C or C++ concepts. Operations and attributes are the declaration, is a declaration part. It is similar to the content of the header files. And the behaviors are the implementation of the declaration. And they are similar to the content of CPP or C files. If we collected use cases and defined our system context diagram, we can continue with the use case analysis with analysis of use case scenarios. Every use case has multiple scenarios in behind, at least two, one basic scenario and one exception scenario. In every system and every project, it is possible that errors occurs, and you need to define the scenarios for this purpose also. What is basically a scenario? Scenario is something like a movie script. You have different participants, you have interactions between the participants, and you have a time order of your interactions. And sequence diagram are very fits very well to these requirements. You have time swim lines, or basically lifelines. You have lifelines. You have interactions between the lifelines represented by messages, and you have the time order. We suggest to define single sequence diagram for single use case scenario. Why? You can say it sounds like a lot of work, and why not to put multiple scenarios into one diagram okay, it would work, but in that case, the diagrams became very fast, very hard to maintain, and very hard to read. So, use case sequence diagrams, the scenarios have different useful outcomes. First of all, they help you, by definition, system interfaces, and they help you collecting system functions or defining system functions. Why? It's simple. Every incoming message represents either operation call or signal, incoming signal. So it is a basis for the system interface, for the definition of system interface. And every operation you defined, it represents a system function. It's cool. So just step by step is a systematic way for that helps you to define the interfaces and to collect the system functions, which are the basis for the functional requirements on the system level and for functional architecture. Let us speak about state machines. State machines are most expressive behavior type in UML and SysML. What does it mean expressive? It means you can express a lot with very small number of elements. The state machine diagrams are very compact and very precise, and basically also very simple. They have very small number of different element types. State machines, they are command centers of your classes, of your systems. They do basically nothing by itself, but they trigger the activities controlled by events, and they decide which event will be processed and will be ignored, depends on the active state. Now to the activities. The activities represent the system functions, and the activities are the implementation of the operation, as already mentioned. So we use the use case scenario analysis, the operations we have collected, and define system behavior for every system function using activities. So, before we continue this with architectural topics, let me spend some words about processing chains. Processing chains, it is one of the most important design patterns for the definition of the system architecture. It is very similar to software design pattern named pipes and filters. And what is it about? What does it mean? Every system has an input and an output, and in between there is kind of a processing. So we have data on the input side, and we have a part of input processing. Then depends on the system complexity, more or less complex application logic in between, and then output processing. And you can, in our case, and in our example, it will be pretty simple. But in real system development, you can also you can define different levels of this chains, processing chains, and structure it in hierarchical way. So let us start with the functional architecture. As already mentioned, we will use the functions, the system functions we have collected during system behavior analysis. The functional architecture is most abstract part of system architecture. So, and why then? Why we need to define it? Why we need to spend the time and that part of analysis? The reason is because the system functionality is the most stable part of the system definition. The technologies changes over the time. You may change the processor type, you may change the hardware, you may change software libraries, but the core functionality keeps the same. Of course, over the time, it could be possible that you will provide new functions, but the core functionality keeps the same. And if you spend the time to develop your functional architecture, that part will be also keep stable and enable you to be flexible during next design phases. It will be the basis for your decision later on. And even if you have already a component design in your mind, just try to focus on the functions of these components and use the behavioral analysis of the system to define the functional architecture. And even here, in that case, you will use you should use this processing chain architecture principle. So, next step, the processing chain architecture on the component level. It is more concrete. You have to address technical constraints in that case, and you have to address also the functional architecture. At the end of after the functional architecture is developed and the chain processing architecture is finished, you should build a traceability between these two types of architecture, or between these two views on the architecture, using allocate relationship. And at the end, you should define the physical architecture of your system. Probably it's the most simple part because it's about real and visible components. There is no software, not that much abstraction. You need to be detailed, too detailed. And here you can also handle the mechanical aspects if it's necessary. Yeah, that's it. And at the end of the day, again, you have to connect to build traceability between the processing chain architecture and the physical architecture, again using allocate relationship. Where at the end of the presentation, and the last slide shows you the meta model of our methodology. Here you see all the topics, all the element types you've discussed, starting with the use cases, use case scenarios represented by interactions with system sequence diagrams, activities, state machines, system interfaces, system functions, system functional properties, system processing chain properties, and system physical properties. So thank you very much for your attention today. And if you mind using our methodology, if you think it could be helpful for you, please contact us. Bye-bye.